let's give it just a minute or two so that people can join up. We are expecting some folks to join us, so we're just going to wait a couple minutes. In the meantime, I will get set up.
Hey, our YouTube live stream is working. Woohoo!
So
That's always hit or miss. Always hit or miss.
David's here.
Hey, sorry, setting up for Riverside. But can everyone hear me? Did I set it up right?
Yes. You
All
good.
right, perfect.
Okay, so we've got all the presenters on. We are live, and let's see. Can't tell if we have nobody's in the chat yet. We've got at least somebody in the audience. Okay, well, the theme of today's webinar is what I like to call Resonate is also. Say what you will about it. It's based off of this parable about the blind men and the elephant. And I know that parable can get a little bit deep into, human behavior and trust and empathy and make some parallels about humanity, etc. But the high level bit of that story is about seeing the whole picture, right? Being able to see the whole thing. If you never knew what an elephant was and somebody came to you and said, hey, there's this elephant, let's go see it, you wouldn't have no idea what somebody's talking about. So at Resonate, we're thinking about what we're building as this holistic programming model for the cloud. And I think it's really easy for people to go, I don't know what that is. So we're kind of going to step back and look at this thing from a bunch of different angles and approach it from angles that maybe are places that you're more connected to. So similar to the blind man and the elephant, somebody walks up and is describing the trunk or the tusks or the ears or the big feet. We're going to try and describe it from a few different angles, and then eventually you'll maybe be able to put the whole picture together. There are 4 different angles that we're looking at Resonate today. Async RPC, the human in the loop use case, which I know we've covered several times, but definitely one of my favorites. I love it, and I love it every time we showcase that. The function as a service capability, Resonate enables that pretty easily out of the box. And task frameworks, Resonate's ability to behave as a generic task framework. So those are the 4 angles that we're going to be looking at today. And I'll be starting us off on the async RPC demonstration and narrative here. And if there are any questions, please feel free to post them in the chat, and we will answer those as we go, and make sure there's time in between demos to answer those. So, yeah, so that's the theme. Let's jump into it. Unless there's any questions. Looking good. So the first angle that we're going to talk about, async RPC, I would say is really important because it does make up this idea of an asynchronous RPC, as I understand it, does make up a pretty big portion of the distributed async await specification. Without asynchronous remote procedure call capabilities, you really wouldn't be able to get this distributed async await specification in totality, I believe. So it's a really major aspect, and that really boils down to your ability to make a remote function invocation. So in code, when you're writing your code, you can do a RFI, remote function invocation, which gives you a promise. And then you can wait on the result of that promise. You could do it right after you get the promise, right in line, and sort of do, make it sequential, or you can wait on it at any other point. So you could put in other code here as much as you want within this function, and get that result at any point, giving you the asynchronous RPC capability. Now, the thing that Resonated does really well and is part of this distributed async await specification is its ability to rebuild the call graph should something go wrong. So this is not super special on its own, but what's super special is if you make this remote function invocation to a service, let's say bar, and bar makes another one or is doing something and crashes, Resonate handles all of that complexity of the recovery and reestablishing the call graph at the platform level. So you're not having to deal with that up here. You can just make this remote function invocation, and all the complexity is shoved into the platform. So I do have a diagram here. We're going to look at three different flows, like execution flows, if you will. So the first is a chain. So you've got a function execution. This would be like foo, bar, and baz. Foo calls bar calls baz. Foo is waiting on basically waiting for baz to complete. Bar is waiting on baz to complete, and so it goes down and then comes back. This chain in and out. If this were to crash, Resonate ensures that this part of the call graph recovers. So I've got a demo here. If we go back and look at, actually real quick, let's go back and look at the code. So here's foo, service foo, which has an HTTP endpoint where you just hit foo, and that will kick off this top level foo function, which then calls the bar function on the bar service, and bar calls baz. And it's just a calculation. So baz returns 1, bar adds to the thing that baz gave it, and then foo adds to that and returns it. Something you would never really ever do. but gets the point across. So we'll run that. So these are 3 independent services. They're independent processes, but you could think of them as running independently anywhere connected by network. We'll send or kick off foo, and oh, it looks like there we go. Sorry. Well, I'm getting a my terminal's having an issue. I think there's a delay at the end. Did I put a 10-second delay in? There we go. Message 3. There we go. So you get the result back. We can do that again. Running Baz, and then we can kill Baz. Oh no, what's going to happen? This service and this service are both waiting on the result. Baz comes back up, and we get the result. So that's pretty cool. Then the other flow we can look at is fan out, what I call fan out. I think most people call fan out, where you send 2 invocation requests back to back sequentially, and then later wait in the result. So it's this right here, where you have top level foo calls bar and Baz, and then waits on the results, both of the results later on. Oops. Right here. So remote function invocation to bar, remote function invocation to Baz, etc. We can, this one will calculate each of bar and Baz, both just return 1, and then foo adds them together and returns that. So just really quickly. Run Baz, run bar, run foo, kick it off, and there we go. The third one is fire and forget, where foo fires off an invocation to bar. Bar invokes Baz, but they don't wait on the result at all. They just fire it off. With Resonate, we do this with a detached API. However, just because we are still in the pioneering stage, this is currently limited to a single node. So detached currently works just on a single node. You can invoke bar and Baz as long as they're local to the process. This will change as we advance the SDK and make that possible. So you can do a detached call to a function on a completely different service, just fire and forget it, and then not wait. But yeah, that's going to be possible as well. I can demo that one too, but really this all would happen in the same process, so it's not very exciting to watch. So it's just the end, the Baz, you basically pass 1 1 1 and then Baz prints it out. So that's going to be possible as well. So you get these 3 capabilities, and then what's cool is you can any particular use case, you can have any arrangement of these, right? A chain, a fan out, fan in, anywhere in this call graph, right? This bar could fan out as well as do a chain and do a fire and forget. So these are the 3 major flows that Resonate enables any combination of together, which is pretty cool. And that basically concludes the demo of this one. See, do we have any questions out there? Let's see, any questions? Dominic, did I miss anything important about this this narrative?
Come on, you can't hand me the microphone. You know I'm never going to give it back, right? But on the other side, I was sitting here 15 minutes quiet and I can't take it. So thank you very much for giving me the microphone. No, you did not. You did not miss anything. But if you don't mind, once again, now that I have the microphone, if you don't mind, I just want to say something about the notion of async RPC. So the notion that the protocol suite that we use to implement the distributed async await programming model actually constitutes an async RPC is, to me, remarkable. And it is especially remarkable if we contrast it to the RPCs that are currently out there. The most prominent example is, just ring it, call HTTP endpoint RPC type, and the other one is gRPC, right? And even though it is RPC, right, remote procedure call, so basically by definition distributed, it is surprising that it does not actually take distribution into account. The only thing it does is it basically allows you to send a message to another machine, right? But it is by no means asynchronous. It actually depends on this physical TCP connection, physical as physical as it gets in software systems. I understand everything is virtual, but on the very bottom, the physical connection, right? So you have process 1, you have process 2. Process 1 opens a TCP connection to process 2, and that tethers the entire chain together, right? And it is by no means async, right? That is a synchronous communication. Even though if you do not, in your programming model, await on the originating process, immediately await, that process via that connection is tethered to the other process, right? So number 1, it is for all intents and purposes synchronous between 2 processes. And it does not actually take distribution into account, right? So it doesn't have any means of coordination other than request response, right? So it doesn't have any other, and it definitely doesn't have any means for recovery. So even though that RPC is basically distributed by definition, it doesn't take distribution into account. It doesn't take partial failure into account, right? If somewhere in your stack you have an RPC or an HTTP call from A to B, right, and that fails for whatever reason, then what, right? There's like, okay, somewhere down in your stack you may get an exception, maybe, probably, eventually. You get an exception, but then what? Nothing is going to help you to recover, right? So it's like, are you going to bubble that up to the application level? Are you bubble that up somewhere to the middle, what you consider a platform level? Can you recover from that? How do you recover from that? All of that is completely left to you, right? So it's like RPC via HTTP or RPC via gRPC is basically like happy path, good luck if everything breaks, right? Tethered together. So it's like the Resonate RPC, the Async RPC actually changes that. The Async RPC, there are 3 protocols stacked on top to each other. The distributed coordination protocol, so that there is no tethering that thing in terms of coordination, right? It's not a request response. You kick something off, and you can await for its value later when it is convenient for you. That's number 1. Then there is the recovery protocol. If the process or one of the processes, as Kali demonstrated, crashes in the middle, right? That particular process will be brought up and the call graph will be repaired. So recovery is a first-class citizen, and that sits on top of the message passing protocol that literally implements only one method, that is send a message. But this method also takes the reality of distributed systems into account because it has 2 addressing schemes. The first one is unicast, where one process sends a message to another process. The other one is anycast, where one process sends a message to any process out of a group of other processes. And it has anycast with preference. Why? Because if you wait for a value, you're basically registering a callback. So Dominic Torno, I am registering a callback. So send that message to me. However, if I'm not available for whatever reason, because I'm sick or on holiday, please send it to any other lovely member of the Resonate team. That is built into the very fabric at the very bottom of the protocol. So the entire protocol suite takes concurrency and distribution serious, makes it a first-class citizen, and addresses it on a protocol level, implements coordination and recovery. So that is what makes this Async RPC so remarkable to me. And we're currently working on a specification. Each and every of these protocols are designed to be dead simple in and of itself. So none of these protocols have more than a handful of messages that are being exchanged. And the exchanges themselves are also pretty straightforward and simple. So, and with that, now it's like, whew, after 15 minutes of silence, I got it out and said everything I needed to say. It's like, so now I'm trying to be quiet again for another 15 minutes. Thanks, Kali.
Awesome. Thanks, Dominic. Cool. So I think next in line is Tomas, who's going to give us a demo and talk about human in the loop again. One of my favorites.
Yeah, this one we have made that a couple times already, but as you said, it's so cool, and I think it's one of the things people will really, really take into consideration when they write their application. So let me share a screen, and you should be seeing my code editor there. Okay, so the way I prefer to think about the Resonate server is that event loop. You as developer get to write sequential looking code, but the code is orchestrated by events. Promises get created, they get resolved, and other processes will be registering callbacks against the resolution of a promise, so they will be notified when the completion happens. And human in the loop is basically just a common abstraction on top of that, where you want to write code where a human at any moment will kick in, resolve a promise, and then your code will be unblocked until with the value the human provided. Usually, the way I have seen that happening is you will have in your API a bunch of event handlers, and when someone resolves that, now you have your logic spread across different event handlers in your system. Resonate, basically everything gets tied into a single core routine. So we have this context of promise that basically what it does is it creates a durable promise on the server that won't be distributed. It will be just existing there in the server in a pending state until the end of time, or when someone comes in and resolves that. Then what we do is, at this moment, we already have a promise ID. So we can take that promise ID and send that through an email. In this example, we are not using any mailbox, but I'm simulating that in the terminal. But you can imagine that being sent through Slack, through email, through SMS, whatever way you want to communicate with your users, employees, whatever. And then what you do is you wait on the resolution of that promise. That might happen immediately, in few weeks, in years. It doesn't really matter. The fun fact is this code will be blocked until the promise gets resolved in the server. And since this process in this example will be registering with a callback, it will get notified and the execution will continue with whatever value the user provided. So the way this works is we will start the authorization for, let's say, Andres at Resonate, right? So an email will get into the mailbox. And hey, you have received an email, and two buttons will appear there. One is to approve, one is to reject. So Andres will say, okay, I authorize that. And this API basically is going to route to this handler right here, where the only thing we do is really just go directly to the Resonate server and resolve the promise with whatever value, either approve or not approve, Andres click on. And when that happens, this coroutine right here will receive that value and either print you're authorized or not authorized. Of course, this is very like bare bones, but you can do a bunch of complex logic there. So in this case, let's say Andres approves the execution. So the API receives the information. It resolves a promise on the server. And then with that value, it kicks again into the coroutine and responds, you are authorized. And that's basically the pattern, which is you create a promise with no distribution, will be just existing there in the server. You somehow communicate that promise ID with the external world, so they can reject, resume, or it doesn't need to be a Boolean. Any value will do. And then you receive whatever information people added as a result for that promise. And now your code looks sequential, but you don't need to worry about like a bunch of logic spread across your application. That's basically it. I don't know if you guys want to add something, but this is more or less what it is.
Nice. I do want to. I'm sorry. Once again, I do want to add something. Very nice. What I want to highlight there is that you can see that the promise itself, right? The durable promise, what this entire thing is built on, is not only a primitive for coordination, right? Here it's a primitive for coordination because the workflow is waiting on that promise and only takes the next step once the promise is fulfilled. But it's not only a primitive for coordination, it is effectively also a primitive for integration. Because as human in the loop shows, the promise does not need to be fulfilled by yet another function, right? So in this case, the promise doesn't need to be fulfilled by another Python function. In this case, the promise is just fulfilled by a human clicking on a link, right? But it also doesn't need to be a human clicking on a link. It can be another system, right? So for example, think of promisifying a Spark workflow. When you create a promise, a Spark workflow kicks off. Right? A data processing workflow. The data processing workflow runs, processes your data, gigabytes, terabytes for 8 hours. And then when it completes, it resolves the promise. And then the promise resolves, your application takes the next step. So your Resonate Python program doesn't even know that it's not waiting on another Python function. It doesn't know that it's waiting on a human. It doesn't know that it is waiting on a Spark job or anything else you want to promisify, right? All it knows is it waits on a promise. And in order for it to be an effective vehicle for integration, we made sure that, once again, the standard for the durable promise himself is dead simple. There are 4 methods to implement. There is create, cancel, if you don't want it anymore, reject and resolve, right? That's about it. That is the functional surface of the promise. So we made sure that the standard for the promise itself is also dead simple. So there is a chance for you to actually implement it from scratch if you want to promisify parts of your tech stack. And if you do, you can use that particular part of your tech stack within your Resonate functions, within your Resonate workflows, as if it was just a part of your Resonate workflow to begin with. So that's super cool about the promises. The human in the workflow is a very, very cool use case, but there is a larger concept behind it, and that is that effectively they're also primitive for integration.
Thank you. If there's no question, I'll start sharing, and I think Andres will showcase, different use cases.
Yeah, thanks, Thomas. So yeah, I'm gonna showcase a different workflow. Let's see, share my screen. You now see the beautiful recursiveness of camera. So yes, as every REST application, it starts with the server. So I'm gonna start the server, right? So I'm in the repo, and it's as simple as, run application serve. The server will start and is running. And then the application that I'm going to showcase, I call it Modulate, and it's basically a function as a service platform, but on premise. You can call it that. So yeah, I'm gonna here start one of the workers. So worker, I'm gonna show the code soon, but just want to show how it works. So the worker is running and waiting for work. And then Modulate itself is a CLI app. So I'm gonna, run. And how it works is you give it modulate, non-modulate.py. And then how it works, you give it a script, right? So in this case, I create this basic script, hello.py. And then you click enter, and it will try to execute hello.py in the GPU. So I added like a bunch of sleeps and whatnot in hello.py to simulate like a long running process. And then it says, okay, the results are located here, and we can get those results out with cap. And yeah, hello Resonate, calculating weights. Like all these days, we are calculating weights all the time. So it calculates the weights and gives the weights. So this is how it works. It has other, let's say, features. So we can hello.py, and we say, I don't want to wait for it. So we say no wait, and it executes, and then say, yeah, you can retrieve this thing back using this ID. So I'm gonna copy the ID, and then I do get, paste ID, and job results are located there, and we do the same. It's gonna be the same result, but I'm just gonna show it to you. It's out. And yeah, we can also, you don't always want random IDs, so you can do ID and say test. I'm gonna use 100 because I tested it so many times. So yeah, it's using now test 100, about 10 seconds. And sometimes something happens, it crashes or whatever. So if you start again, and the results are already ready. So yeah, recovery and coordination. So let me show you the code. So let's start bottom up by showing you the script. So this is the script that hello.py just a bunch of print statements. Then I'll show you the worker. So this is the worker. And as you can see, it's a single function here, execute. But it's been, this is not even started, it's just resonate that got it started and registered this function. And the worker is kind of waiting for work. And it's a very simple function. It just calls Python with the script. It gets the content of the script. We are not sending like, oh, the script is in this file or anything. We're sending the whole content of the script. And then we write this script to a file, a different file, and then execute it with Python with some, flags that make sure it's isolated and doesn't read like the environment and whatnot. So for security, you can imagine this being, instead of Python, like a Docker file. You send the Docker file, or you kind of the path to a Docker registry or something, and you execute it that way. So it's just a function that has this flag here, or this tag here to register it, or decorator. It's called in Python. I almost had a seizure there. And now let's go through the main application. So you can see here all this code here. This, I don't know how many lines. Is just parsing the flags. So parsing the flags is longer than executing this thing in a distributed fashion. So once we have the args, what we do is we call this function prep execute with the argument. So we wait or not, and we pass the script here and the machine type we want to execute. So let's go to prep execute. And prep execute reads the content of the file. And well, we can see that this is important. The decorator has a way to register like the options. So we say, we don't want to retry this thing, never. If it fails, it fails. I don't care about retry policy here. But in the other one, in the other file, in the worker, you saw I didn't define one. So it kind of uses the default, which is an exponential retry policy by default, but you can define, we have several: linear, exponential, never. So here, as Collie said before, we had detach, and detach only works locally, but I wanted a detach that worked remotely. So what I did, I implemented my detach RFI here, which basically is a detach that is local but calls an RFI function and doesn't await for it. So this kind of simulates, or this is actually detach remote implemented in user space instead of being provided by the SDK itself. It's not fully, fleshed out as it will be once we have it like as part of the SDK, but it kind of gets the job done. So we are, as I said, written content, and we either, if we have to wait, we call it with this function RFC, which is remote function call, when we wait for the result and return the result, or we call it in a detached fashion, so we don't have to wait. And here we define execute, right? And it's basically as a C declaration. We define it, and we don't give it a body. But when the server sends it, the worker will have the implementation of it and being able to execute it. So we call here execute, and we use it mostly to get nice type completions as well, not when we use it here. So if I don't know, give it an ID, right? So if an ID, it will complain, right? Let's see. It should complain soon. Well, whatever. It sometimes, yeah, Pyrite is not running. Sorry about that. But yeah, you get nice completions if you do it, or you can pass a string. And yeah, this is kind of the demo. I can also, just to show you that the stuff is not, made up, I can change here for hello webinar, webinar, right? And we run it again here, modulate hello.py, and let's say test webinar. And let's do no wait, because I want to show a node feature as well. No wait, and if I'm fast, I can show you. So get test webinar, boom. Yeah, webinar is not ready yet, right? So we are, okay, let's run again. And now it's ready, and we can cut the results. Test.webi, test.webinar out, and boom, hello webinar. So yes, I think this is what I wanted to show you about Resonate today.
Okay, number one, this is pretty awesome. Number two, I want everybody to appreciate that Andres put the subtle joke in there. I was like, oh, I gotta do a machine learning demonstration, and I'm gonna calculate some weights. And the first time he showed it to us, it was like literally saying 10 kilograms, 12 kilograms. I was like, at first I completely missed it. I was like, oh my God, he calculated weights. So I thought that was pretty cool. That's the only thing I have to add there, because it's like we cannot have it that this joke went unnoticed. I thought that was really awesome. But the demo is also really, really awesome. Very, very nice. Thank you very much.
Yep.
All right. Well, that brings it to me,
thanks,
I
Andres.
guess.
Kick it off, David. Go for it.
All right. So I had the task of Resonate is also a task framework. I'm just going to jump right in. Let's just jump right in and look at a running example. Oh, I might have to restart and come back because I don't have permission to share my screen. Okay, I will be right back.
I want to say that David there tried to reclaim the crown for the joke by saying his task was writing about tasks. So it's also not bad. I still like the weights better. So the weights was cooler, but not bad. That's a close second.
Awesome. I want to publicly apologize while I have a minute to the folks who might have joined the Zoom link that was on the calendar invite that got created accidentally. In case they went there instead of here. That would have been on me. I missed that. So I think a couple folks might have accidentally ended up in a dead Zoom meeting. Hopefully they find their way here. They did find their way here.
This will be in YouTube, right? Anyway.
Yeah, I mean, we're recording this, so.
Yes, but still not a great experience
No,
when you're waiting on a Zoom meeting.
Not the worst either.
Awesome, David. You okay to share now?
Yeah, let's see if it works this time. Oh, okay. Sorry about that. Oh, there's the recursion again. Okay. Resonate is also a task framework. So what is a task framework if not? Wow, that is really cool. That's tripping me out. If not distributing workloads to workers. So how about I'll show a very quick example of the finished product, and then we can dissect it and look at the individual components that come together to build this application. So what this is called Resonator. Resonator is a distributed calculator. And if I start it over here in the leftmost window pane, I get a prompt that I can put in a mathematical expression. There are some boundaries to the symbols that are permitted. We do only operate on integers, and the only supported operations are addition, subtraction, and multiplication, which keeps us bounded in the set of integers, which just makes things a heck of a lot easier. And I also want to preface this with the Resonator calculator uses a regex to parse the expression itself, and that regex is not fully tested. So it doesn't do things like respect order of operations and stuff. So if you want to truly use this as a calculator, you will see incorrect calculations. But really what we're trying to do here is we're trying to show the distributed nature of Resonate and what you can build with Resonate. And that, I feel like, is shown, even if the actual answer is not the exact right answer. That being said, order operations is stupid and arbitrary anyways. Okay, so I've got a prompt, and I'm going to run a quick calculation. We're going to run 1 plus 2 plus 3 plus 4. And I am running the calculation in the leftmost, let's call this the main window. And I've got a bunch of other windows open simultaneously and already running. These are our workers. We've got 2 workers connected to the EXP group, connected as LHS for left-hand side and RHS for right-hand side. And then additionally, we've got 2 more workers connected to the ops group, and this time with no PID specified. So they're just generically connected to the ops group. All right, so let's just go ahead and run this and see what happens. All right, so what is happening here, and I'll show in a sec, is the expression is broken up and distributed to workers. So the left-hand side connection on the EXP group received the left-hand side of the original expression, 1 plus 2, and the right-hand side connection on the EXP group received the right-hand side, 3 plus 4. 1 plus 2 contains nested expressions, 1 and 2, which recursively distributed the task once again to the left-hand side and the right-hand side connection. And the same goes for 3 and 4. 3 was distributed to the left-hand side, 4 to the right-hand side. And finally, once all sub-expressions were fully evaluated, we could then perform the mathematical operation. In this case, our expression contained only addition, so we ended up with a couple different addition operations, and those were handled by any connection on the ops group. And since no preference was specified, the addition could end up being processed by any worker. And in fact, if you don't specify, we choose a worker randomly. So in this case, the first one got 1 addition operation to calculate, and the second one got 2. And the final result was sent back to the original command prompt, and we got 10. And I do believe that is correct. So that one is correct. Of course, that one, order of operations don't really matter. Anyways, okay. So what is happening here? How is this implemented? Well, you probably guessed already. It's implemented with Resonate, and it's implemented by defining our operations. These are base operations that get invoked when all sub-expressions has been fully evaluated. We have add, sub, and multiply. And notice that there is nothing special about a function, a worker function. It's just a function. For Resonate to be able to distribute these workloads to worker nodes, the only requirement is that you register it with us and you optionally name it. If you don't name the function, we'll take the function name itself by default. In this case, I have gone to the extra step of naming it with its corresponding mathematical symbol, so that I can just easily look up that function from the expression, because you're using the plus sign and the minus sign and the asterisk sign in the mathematical expression. Okay, and there is a single calc function that that ties this all together and distributes tasks to workers. And that's happening here. Now, I'm kind of cheating a little bit, and the calc function can be run in two modes. It's either run in worker mode or it's run in prompt mode, where I'm like printing stuff if it's run in worker mode and not printing stuff if it's run in prompt mode. That being said, there is fundamentally no difference. It's just a calc function. It doesn't matter if it's the start of a workflow, if it's a nested step within the workflow, if it's running on the main node, if it's running on a worker node, it is just the same function. So what we are doing is, before we ever run the function, we are receiving a parsed expression. The parsed expression is a nested tuple of operands and operations. So the operations are the three that we defined above: addition, subtraction, multiplication. And the operands themselves are either a integer value or a nested expression. Once again, an operator and two operands. And what we are doing with the left-hand side and the right-hand side operands is we are recursively calculating them, evaluating them by sending the task to the exp queue, or for the case of the right-hand side operand, well, also the exp queue again, but this time preferring the RHS connection over the LHS connection. This is a preference, so I would like to show, if I go ahead and I kill my RHS connection and run another calculation, this time just simply 1 + 1, then everything is going to happen on the LHS side because there was no RHS connection. Okay. Then finally, once the left-hand side and right-hand side operands have been fully evaluated, we will await on the final value by simply yielding the promise back to Resonate to get that final value. Now, there is a lot happening here. Like, this is recursive. So the important thing to note here is that when we yield the promise, we are guaranteed to get back a concrete value. At this point in time, the expression has been fully evaluated to an integer. And that's actually what's happening down here. There is the case that the expression is already fully evaluated. And in that case, rather than a tuple, it's just an integer. And we just return the integer. So that is really, really cool. Like I really want to stress this point. When I run my program in the prompt, I run the calc function. When I run my program in the workers also just run the same calc function. There is no differentiation between a workflow and a step, or maybe a workflow and activity. It's all just recursive functions all the way down. And when I get an integer value, I now know that I can execute the mathematical operation. And this time, I am sending it on the ops group with the two fully evaluated operands. And here, I'm yielding an RFC rather than an RFI. There's a semantic difference there. So an RFC awaits a value, so a final integer value, rather than awaiting a promise. I'm basically just shortcutting or skipping ahead to the final value rather than get that intermediary promise. And then one more thing I really want to stress here is that the second, or in this case, the third call to context.rfc down here is composing the result of two previous tasks. It's subtle and it's very easy to miss it because oftentimes task frameworks will have their own DSL or their own semantics for chaining together two tasks, taking the results and then sending them to a third task. But in Resonate, it's just the function call. So it's very easy to miss because we're all just used to function calls. They're very natural and easy to use. But because Vx, and Vy are coming from the result of two previous tasks, I am, in effect, chaining together two tasks with a subsequent task. And yeah, that is everything. Then you get a final result and you just return the final result. So one more time, maybe I will show Resonator again. Let me start up the right-hand side connection before I do. And let's do a little bit more of a fun calculation. So I'm not even sure what answer we'll get here, but let's just run this. Okay, I chose this one.
Your luck.
Yeah, right. I chose this one because it's pretty balanced. It's really cool. You get to see something on the LHS come in at the exact same time as something on the RHS. All right, there we go. We get 16. I don't know if that's correct. I hope it is. Someone watching can grab a real calculator and let me know if Resonator is correct.
Paste it into ChatGPT. I heard it's good at math.
Paste it into another thing that's not a calculator.
That could be me. Yeah, it's like me in 11th grade. Let's say 6th grade to keep some of my dignity. Awesome. Thank you very much. I wanna really hammer home one thing that David said at the very end. So if you are a Pythonista, yeah, then and you are used to task framework, then your poison is probably Celery, right? So if you go to the Celery website and you look at the canonical example that Celery has on the website, they also do mathematical calculation. They add two numbers, right? So they schedule a task of adding two numbers, and then later they are retrieving the result. So this is including the setup, including the configuration of everything in your Python script. This is a few lines of code. And like defining the task is like one very simple function. Starting the task is one very simple function call. Right? If you do that with Celery and you put the code for Resonate right next to it, it basically looks the same. So instead of instantiating an instance of Celery, you instantiate an instance of Resonate, and that's basically it, right? So it looks very much the same. The same thing happens. You take the request of your computation, you put it on one of these workers, and then later you get the result. So, but that's where the honeymoon of simplicity ends. Because then it's like, what happens if your workflow is not only one task, right? Then that is exactly what David mentioned, that a lot of these frameworks have their own DSL, right? And and I by no means want to drag Celery. It's a very capable framework, and it's obviously also a very popular framework. So, but once you want to compose something into larger workflows, you have to like understand a lot. You have to start learning about groups and chains and chords and star maps and chunks and signatures and partial and links and error links, right? So that is a whole universe of things you have to like understand in order to start composing small individual tasks into larger tasks, right? But not with Resonate. It's a function, right? Just as David showed. And a function calls a function calls a function calls another function, even if it calls itself recursively, right? There is no DSL here. There are no chains, no chords, there are no workflows, there are no activities. They are just functions. And if you want to use them as a task framework, you can start a function on another node awaiting its result, right? And that function can start on another node awaiting its result. And you can, of course, also target certain groups of nodes. Like, for example, I want this not to run on any generic node, but on a node that has GPUs available, or on a node that is attached to a certain hard drive. You can basically, you can state where you want to execute it. But on a simple and high level, the point still stands. It's a task framework because you can distribute the individual tasks to different machines. However, it also has a great developer experience because you can just use functions in order to compose other functions. Thanks, David. It was a very nice demo. The resonator.
It's turtles all the way down, except
turtles all the way down. It may distribute mathematical expressions. It may not give you the right answer, but it will distribute it across your cluster. What's that say? Maybe I'm glad we're in that to calculate Andres weights. Boom! Full circle.
I'm glad we're in agreement that order of operations is dumb. I'm saying we're all in agreement.
We were not in agreement with that. I am very sure that most people are not in agreement with that. But before the chat actually blows up, I think we are already 2 minutes over time. So I don't want to. I'm handing back the microphone to Cully, because Cully was our MC today. So it's like, now I'm gonna shut up.
Cool. That was great. Thank you. Thanks everybody for showing up. Thanks, David, Andres, Tomas, for presenting. Really appreciate it. I hope that looking at Resonate from these different angles helps shine more lights onto this thing, and shows the elephant for what it is, hopefully quite a bit more for the folks out there. And if anybody watching would love to know more, get involved, please join our Discord. There are links on our website. I think Dominic's going to drop the link in the chat right now. That's the place to hit us up. We're very active in there with the community. Would love to chat with you. And we'll look forward to seeing y'all next time. We're planning to do this
again. There's a question.
Oh, hold on.
Yeah.
Oh, that was a very nice question. Hey, Brett, that was a very nice question. I don't have an answer for it, but it's a very nice question. Definitely made me smile. I think if I look at all the faces here, it made all of us smile. Thank you very much. That was a very, very nice, very, very nice conclusion of this webinar.
I was going to save this for the Discord, but Brad, I think you've earned yourself a champion badge for being the one person who's attended to every single one of our webinars thus far, and been incredibly supportive. So thank you very much. And we'll definitely look forward to working with you more. All right, cool. Thank you so much. I think that's a wrap. We'll see you next time.
Awesome. Thank you.
Thanks, everyone. Bye, everybody.
Bye, guys.